Hello and welcome. In today's video, I'm going to be going over 100 derivative and limits of Christmas slash Newton's birthday. So, for those of you that don't know, Newton is a mathematician who was born on Christmas, but he is also very important to calculus. So, to kind of celebrate this fact, I have gone through and arranged 100 calculus problems, more specifically limits and derivatives. So I'm going to go through all of these problems just as a nice little refresher. And if you need to work on some practice problems for any test maybe that you're taking or just for fun like I'm doing, then you can have all of these practice problems right here for you. I got the majority of these practice problems from the book Calculus Early Transcendentals, 9th edition. By James Stewart. And then some other calculus or some other problems from Calculus 6th edition from Hughes Hallett. I don't know if I said their name right, but Calculus Single Variable, in all honesty, a really good textbook. The one that I use in my actual calc class when I'm not teaching it. So, to kind of get started here, as we know, we're going to have to work our way through this. A limit of a function, of a composite function, is equal to the composite of the limit of x squared plus 3x. And I'll change my color here in a moment. And if this limit goes to 0, that means that we're evaluating cosine at 0. Cosine at 0 is 1. Alright, continuing on. This next one, I believe we need to see if we can plug in 3. If we plug in 3, we get 9 squared minus 9, so that's 0 over x squared, so 9 plus 6 minus 3. Well, that's just 0 over 12, so that's just 0. For this next one, we're doing as x approaches negative 3 of the same thing, so once again we get 0 in the numerator, but in the denominator we get 9 minus 6 minus 3. So this is a 0 over 0. So what we want to do here is factor out an x minus 3 and x plus 3, and then factor the denominator. In this case, the denominator is going to factor to x plus 3 times by x minus 1. Now we are going to cancel, and now we can use direct substitution to see that negative 3 minus 3 over negative 3 minus 1, that evaluates just to negative 6 over negative 4, or 3/2. Alright, for this next problem, we are now going to try and find the limit as x approaches 1 from the right of the same situation. However, we know that because 1 in this case is going to be a 0 in the denominator, we can't direct substitute it. So, what we're going to have to do is just see what happens here. So we are going to have x squared minus 9 all over what I'm going to say is x plus 3 x minus 1. Okay, so if x is approaching... So we know that this denominator is going to go to 0 no matter what, because there's nothing in the numerator to cancel it. So what we can do is we can still leave these three x plus 3's canceled, but we can be left with x minus 3 over x minus 1. Now we can start plugging numbers that are really close, but a small bit greater than 1. And we see that this denominator is going to be slightly positive. However, the numerator is going to be negative. Because this is the case, a negative divided by a positive is going to be a negative. And because we know this is going to 0, this is going to be an asymptote. So we are going to say that this is going to be negative infinity. Alright, for this next one, interestingly enough, this is just a definition of a derivative. So we are going to, instead of using like any rules to like expand this out or anything, we are going to just say that f of x is just equal to x cubed. Alright, and then looks like they were evaluating this at, or actually, this is slightly not the definition of a derivative, but I think I can get around that. Well, let's see. So really, this is just f prime of negative 1. Because negative 1 cubed, that would be the part that we're subtracting off, and then h minus, that would be our x plus h, where x is negative 1. And we know that this is really just f prime of x is equal to x cubed. As thus, if we want, or sorry, not f prime of x, but f of x. So f prime of x is equal to 3x squared. We can now plug in negative 1 for the x, and what we get is it's equal to 3. So that's our answer. Alright, for this next one, looks like we have a difference of cubes and a difference of squares. So in this top, we get t minus 2 times by t plus 2. And the denominator, we get t minus 2 times by t squared plus 2t plus 4. The t's minus 2 cancel, so this is no longer 0 over 0. And this leaves us with t plus 2 over t squared plus 2t plus 4. Alright, now what do? We just have to plug in. We get 4 over 2 squared is 4 plus 2 times by 2 is also 4 plus 4, that is 12. So our answer is 1/3. Alright, for this next one, we want to know what happens as the limit approaches 9. I suppose I should make this a small bit more clear, of square root of r over r minus a cubed. Good question. Well, the way that we're going to do this is we are going to first try to plug it in. Well, we get 3 in the numerator, but in the denominator we're going to get a 0. Now, is there really any way of us maybe canceling out a term here and maybe solving this? And the answer to that question is no. So this limit does not exist, as no matter which way we try to break down this denominator, it's still always going to approach 0. Alright. Now I've got a few more limit problems for us, and this one you might recognize. So we're taking a limit of 4 from the from the right, the limit as v approaches 4 from the right, of 4 minus v over the absolute value of 4 minus v. So, what is this going to look like? I would actually like to kind of do this one a small bit more graphically. So we know that for most values, for all negative values up until our 0.4, well, this v is going to be slightly small, the numerator is going to be positive. Because we're subtracting off this v. So as it approaches 4, it's going to get closer to 0, but it's going to be positive. This denominator is going to be the same. It's going to stay positive. So we know that this is going to be like somewhere up here in the positive direction. But this denominator, well, let's look at it from the right now. Well, as you look at it from the right, since we're now subtracting off v's that are greater than 4, this numerator is going to be negative, but the denominator is going to be positive. Because of that, we are now going to get a negative number. But because we're still dividing like something on the terms of x over x, this is just going to really be the limit as x approaches 4 from the right, which in this case is going to be negative 1. Okay. Got another one here. So if we plug in negative 1 to this problem, we get 1 squared, which is 1, minus 3, or plus 3, which is 4, minus 4, that's 0. Okay. And then in the denominator, we're going to get 4 minus 1 minus 3, that's also 0. So this is 0 over 0. What are we going to do with this? We're going to see if we can factor it. Well, the numerator is going to factor out to be r minus 4, r plus 1 over, and this denominator, let's see if I can still do this. We want to find something that multiplies to 12 but adds to 3, or sorry, not 3 but 1, and the numbers that are going to do that are 4 and negative 3. So we once again just do our box. We know that we have a 4r squared, we know we have a 4r, a negative 3r, and then a negative 3. So we know that this is going to be negative 3, this is going to be 4r, then we're going to get r and 1. So what we get is 4r minus 3 times by r plus 1, which cancels, meaning we can now evaluate this limit. R minus, or negative 1 minus 4, that's just negative 5, over negative 4 minus 3, that's negative 7. That's going to be 5/7. Alright. So, let's see, we now have another problem here. Accidentally erased it. There we go. So, this looks like another definition of a derivative, surprisingly. But we're not going to evaluate it like that. Instead, we're going to multiply the numerator and the denominator by the conjugate of the numerator. So it's going to be 3 plus the square root of t plus 4 over 3 plus the square root of t plus, or actually I believe this is 9. Oh wait, no, that is 4. That's the only way that this will make sense. Okay. So, after we do that, we get 3 minus t minus 4 I was kind of expecting those to cancel, over let's see, we have t minus 5 times by 3 plus square root of t plus 4. Alright. So now simplifying the numerator, we are going to get a negative t minus 1, if I can do math, over 3t plus t square root of t plus 5, and then minus 15 minus the square root of t plus 5, or t plus 4, sorry. Okay. You know what? We're going to try a different approach, because even though this will work eventually, we're going to have to do this more than once. So, I'm going to use a Hospital's rule, because this is going to be a 0 over 0 indeterminate form. So, because 5, that would be 9. So yes, this is 0 over 0. So we're going to take the derivative of the numerator, the limit as t approaches 5 of negative 1/2 square root of t plus 4 over the derivative of the denominator, which is negative 5. Well, in this case, we are going to get a negative, or actually we're going to cancel those negatives just to make our life just... Also, it should only be 1 in the denominator, but okay, so we have negative 1/2. Then we can just plug in our t's equal to 5 directly, and we get negative 1/2 over 6. So our answer for that derivative is 1/6. I realize my original method is kind of confusing, but I digress. For this next one, I believe that this is more of a dominance problem than a Hospital's rule, even though you can treat this as a Hospital's rule. I don't know if I actually say his name right, but L'Hopital. There it is, L'Hopital. I don't know why I always like to call it Hospital, but it's L'Hopital. So we have x squared minus 9 over 2x minus 6. So, of course, you could do something with this. Would I recommend it? No. So, let's think of it like this. As x goes into infinity, this negative 9 and this negative 6, they're insignificant. So we're going to look at the two things with the highest degree. And you might notice that even though this this numerator is in a square root, if this negative 9 and this negative 6 are insignificant, this is going to start looking like the square root of x squared over 2x. Okay. And the square root of x squared is just x over 2x. So what you'll see is as you're taking this limit to infinity, these x's cancel, and it's going to approach 1/2. All right. Now we want to do the same thing, but instead we're approaching negative infinity. Well, once again, this is dominance here. So then as we go out to negative infinity, once again, this negative 6 and this negative 9 aren't going to be relevant. So what we do is we're going to plug in, or we're going to just say that this numerator is going to become something close to the square root of x squared over 2x. Well, technically this is the absolute value of x over 2x. So whenever we're going out to negative infinity, this numerator is going to be positive but the denominator is going to be negative, so this is going to go to negative 1/2. This next one is another composition, and it's the limit as x approaches pi from the left of the natural log of sine of x. Okay, so let's get started here. So, we know that this is going to be the same thing as the natural log of the limit as x approaches pi from the left of sine of x. Okay. Well, what is the limit as sine of x approaches pi? Well, in this case, sine of x is going to approach 0. So, as this sine of x gets really close to 0 from the left, well, let's see. This limit shouldn't exist, should it? Because, wait, no. It should have a positive out. Never mind, scratch that. It's just going to be very, very close inputs to 0. So this natural log of x, of the sine of x, these sines of x's are going to be getting really close to 0, but they are going to be positive. So this natural log of x is going to be the natural log of 0, which the natural logarithm has an asymptote at 0. In fact, it has a negative infinity asymptote, or infinite. Yeah, an asymptote that goes to negative infinity. All right. For this next one, we have the limit as x approaches negative infinity of 1 minus 2x squared minus x to the fourth over 5 plus x minus 3x to the fourth. Once again, this is dominance, even though this is approaching infinity and you can technically use L'Hopital's rule. This is more of dominance. You don't want to do more work than you have to. So what we can say is the term with the highest coefficient or the function with a higher magnitude is going to dominate. So we just need to look at the functions with the highest magnitude. So this negative x, so as this goes to infinity, we only need to look at this negative x to the fourth and this negative 3x to the fourth. Well, as we approach negative infinity, these are just the same number. So we get a negative 1 over negative 3x, or negative 3. And if that's the case, our limit's going to approach 1/3. All right. Next up on the list, we have the limit as x approaches infinity of e to the x minus x squared. So the way I would like to do this is I'm actually going to rewrite this using exponent rules. So we're going to get the limit as x approaches infinity of e to the x over e to the x squared. Now, what you may notice as x goes to infinity, this denominator is going to grow a lot faster than the numerator. As thus, this limit's going to approach 0. As whenever you're dividing by a bigger and bigger number, it's going to get closer to 0. All right. Now time for the limit as x approaches 0 of tan inverse of 1 over x. So the way that we want to think about this is really just tan inverse of 1 over x. So, how is this going to work? What's going to happen? Or the limit as x approaches 0 from the right of 1 over x. Okay. So this limit here, what is this really going to be equal to? Well, this limit is going to be really the same thing as infinity, as we're only dealing with positive numbers. So we're going to be taking the tan inverse of infinity. You may recall that tan inverse actually has a horizontal asymptote. So as x goes to infinity, tan inverse is going to be approaching a certain number, and that number is pi over 2. It's going to approach pi over 2. So this is kind of scary, especially for those of you that have dealt with the epsilon delta definition before. But we want to prove the following using the epsilon delta definition of a limit. Very scary, I know. All right. So for this first one, we have, or just as a refresher, for any epsilon within like a range of L, which is the predicted value, then there is a delta such that x minus a is less than delta. All right. So we're going to take the limit as x approaches 2 of 14 minus 5x is equal to 4. Okay. So we know that our function, so our absolute value of 14 minus 5x minus L, which is 4, is equal, or needs to be less than our epsilon. We also know that x minus 2 needs to be less than our delta. So the way that we're going to find our delta is by solving for this epsilon. So what we're going to find is we can simplify this a little by calling this 10 minus 5x. Then we are going to factor out a negative 2, so we're going to get a negative 5. So we are going to get x minus 2 is less than epsilon. And now you may recall that you can choose this epsilon to be any value you want it. So if we want it to be 0.01, we can say it's 0.01. It's however far away from our function we want to be, or how close we want to be to our actual approximation. Well, I digress, as I'm not going to be actually plugging in any values for this. It's more or less just walking through the process. The absolute value of negative 5 is 5. The absolute value of x minus 2 is just x minus 2. Is less than epsilon. Now we just have to divide the 5 to the other side. So we get our epsilon is like epsilon over 5, and we find that we now have an expression that is the same as our delta. So we know our delta must be less than epsilon of 5. So that's really saying that if we want a value that's within epsilon of L, then we need to choose a delta such that delta such that delta is less than epsilon divided by 5. Alright, now for a bit more challenging of one. So we know that we are going to start by choosing or finding out what we need to find. So we want our absolute value of x to be less than our delta. And we want f of x, which is the cube root of x, minus 0 to be less than epsilon. Alright, what are we going to do here? Well, I think it's safe to say that since we're dealing with absolute values, maybe we want to break down this epsilon. Maybe. Because I can't really do anything with this just yet. So we're going to say that we have a negative epsilon is equal to the square root of x is less than epsilon. Okay, now what? Well, we now need to cube everything. So we're going to raise everything to the third power so we can maybe get a absolute value of x back. So we're now going to get the negative epsilon cubed is less than x is less than the epsilon cubed. Alright. Now what? Well, we can use our very properties that we used originally to unmake this inequality, to make it more look like our delta. So we're now going to say that because of our inequality properties, we can call the absolute value of x just the absolute value of x less than epsilon cubed. And because we now have this value, we know that our delta must be equal or less than epsilon cubed. Or equal to epsilon cubed, really, but if you want it to, it can also be less than. Alright. This is just one of those theorems of calculus. So our goal here is to use the intermediate value theorem to show that there is a solution in the interval. So for those of you that don't know, the intermediate value theorem states that if f of x is a continuous function, then it's kind of hard just to say, but if f of x is continuous on an interval from a to b, and there is a number c in the interval from a to b, there must be a f of c that is in between f of a and f of c. Or sorry, f of a and f of b. So really, it's just saying that f of a must be less than or equal to f of b must be less than or equal to f of c. Or f of c, sorry, in the middle. F of b. And the reason for that is it's kind of continuous, so no matter what, it's kind of hard to explain, but we'll make a video on I think I already have made a video on the intermediate value theorem. I think it's a very cool theorem. So to start out, we're just going to plug in 1 to find out what f of 1 is and f of 2 is in these intervals. So f of 1, in this case, is going to be 1 minus 1, which is 0, plus 3, which is 3, minus 5, that's negative 2. Okay, so we know f of 1 is equal to negative 2. We also know that f of 2 is 2 to the power of 5, 2, 4, 8, 16, 32. So we have 32 minus 8 plus 6 minus 5. So we have 24, 30, 25 is our f of 2. So there must be a number c because the function is a polynomial. The function is a polynomial. And as thus is continuous, on the interval from A to B, and f of 1 is less than or equal to 0 is less than or equal to f of 2, there must be a c value c such that f of c is equal to 0. And that's what you do for the first one. Now on to the second one. So, once again, we need to plug in our values on the interval. So, cosine of square root of x, well, cosine of 0 is just 0, or is just 1. So we know 1 is equal to, and I suppose I want to subtract this stuff over to the other side, but e to the 0, which is 1, so negative 1. Add that over to the other side, and we get 2. So if we call this f of 0 is 2. Okay. Kind of bad math, but that's how it works. Now, we're going to plug in f of 1. So the cosine of 1 is a number I don't want to deal with. Is equal to e minus 2. Well, we know e is like 2.718 or something like that. So minusing 2 from that, that's going to be like 0.718. I'm guessing cosine is still slightly bigger than this. So we're just going to say less than 1, or a small bit less than 1. And because of that, or actually I can probably find this out. Give me a moment. Trig cosine of 1 yeah, 0.54 minus e minus plus 2. Okay. And then if you subtract all of this over to the other side, we get f of 2 is equal to negative 0.178. Alright. So, because these values, one is negative and the other is positive, and this is a continuous function, there must be a value c such that, in between 0 and 2, such that they are equal to each other. The expressions are equal to each other. So because the function is a trig it's a trig function. It is continuous for all points in its domain. I should have really said exponential / exponential. Alright. On the interval, roll from 0 to 2. And f of 0 this is kind of just a strange way of saying this, but f of 2 is less than or equal to 0, which is less than or equal to f of 0. There must be a value c such that f of c is equal to 0. Alright. Continuing on. We have... Okay, so we want to show the following are continuous on the domain. So this is really just going into the definition of continuity. So what we're going to do is we are going to show that via direct substitution we can find any value. So we're going to take the limit of f of x as x approaches a and see if that equals f of a. So for this first function, this limit, or f of a, is going to be a e to the sine x. The limit as x approaches a, because this is continuous, we can just plug it in. We get a e sine of x, or sine of a. Both of those should be sine of a. I don't know why I did sine of x. And because this is true, this function is continuous. For the next one, if we take the limit as x approaches a of f of x is equal to f of a, and that's my very strange spot on my tablet where it loves to die, we see that this limit is going to be 3 times by a cubed plus a squared plus 3a. Well, and that must be equal to, well, f of a is equal to 3a cubed plus a squared plus 3a. They are equal. All right. For this next one, tangent of x. Once again, we take the limit of both sides. So we take the limit as x approaches a of f of x is equal to f of a, and see if that statement's true. Well, the limit as x approaches a of tangent of x is tangent of a. The f of a, however, is also tangent of a. However, I would like to state that this is only going to be true for whenever tangent is defined. So even though all the majority of functions that we know are continuous when they are defined, continuous when they're defined, but not all of them are defined for all real numbers. Alright, continuing on. And that was the last limit. All the rest of these are derivatives. So this is going to be a very fun time. A lot of derivatives to work through. Okay, for this first function, we have to apply the chain rule. So we are going to get y prime is equal to 4x squared plus x cubed times by the derivative of the inside, which is 2x plus 3x squared. And that's our answer. This next one, we can either treat it like a quotient rule, or we can do something a bit simpler. So we're going to say f of x is actually equal to x to the 3/2 minus x to the 1/2 plus 2x to the -1/2, We're just distributing the square root of x. And now we can take the derivative of this. And we will get f prime of x is equal to 3/2 x to the power of 3/2 minus 1/2 x to the negative 1/2 minus x to the negative 3/2. All right, next one. This one is a product rule. G prime of x is equal to, the derivative of the first is 2x sine pi x times by the derivative of, not times by, but plus the first, which is x squared, times by the derivative of the second, which is going to be cosine pi x times by the derivative of the inside, which is just pi. Bringing the pi out front, we get pi x squared cosine of x. This next one, we all know we hate the derivative of the inverse trigs, but we got to do it. So y is equal to x sine inverse of x. So if we take the derivative of this with respect to x, we get y prime is equal to the derivative of the first, in this case, is sine inverse of x, plus the derivative of the second, plus the first, x, times by the derivative of the second, which is the derivative of sine inverse of x, which we know is 1 over the square root of 1 minus x squared. And that's our answer. We can't really simplify it any more than that. All right, next questions. So now we have to deal with some implicit differentiation. So we're going to once again take the derivative with respect to not x, but y. No, I'm kidding. We're doing this with respect to x. But anyway, we're going to treat this left side like a product rule. X, the derivative of x is just x, so it's 1 times by e to the y, plus x times by the derivative of the second, which is going to be e to the y, times by the inside function. In this case, it's going to be dy dx. Okay. Now, on this left side, once again, it's a product rule. We're going to get dy dx times by sine x plus y times by cosine x. Okay, now what do? We need to get all of our dy dx's to one side. So we're going to get x e to the y, dy dx, minus dy dx sine x is equal to e to the y minus negative, or y cosine of x minus e to the y. And now we just need to divide this x e to the y minus sine x to the other side. So after factoring this, dy dx, dividing it over to the other side, we get dy dx is equal to y cosine of x minus e to the y over x e to the y minus sine of x. Sadly, there's not much more we can do to simplify that. Next one, we have t is equal to the natural logarithm of x ln of x. Once again, we take the derivative of this with respect to x. So we get dt dx is equal to the derivative of the natural logarithm is just 1 over its argument, x natural log of x, times by the derivative of the inside. The derivative of the first is the natural log of x, plus x times by the derivative of the second, which is 1 over x. Because I don't like fractions and fractions, I'm going to multiply the numerator and the denominator by 1x. So we are going to be left with dt dx is equal to x natural log of x plus 1. Or actually, scratch that, I realized that there was a bit of simplification I could have done earlier. X times by, or dt dx, well, the natural log of x is just the natural log of x. X times by 1 over x is just 1. All over x natural log of x. Okay, now what do we do? That's it. That's it for 31. Now let's work on problem 32. Alright. We have y is equal to e to the mx cosine of nx. Well, I'm guessing this m and this n are just constants, so our y prime, the derivative of the first is the derivative of the first is going to be m e to the mx times by the second cosine of nx plus the first e to the mx times by the derivative of the second, which is negative sine of nx. And here's our answer for us. Alright, next problem. We have, wonderfully enough, a quotient rule. Gotta love quotient rules. I definitely don't. They're my least favorite. So the derivative of the top in this case, so we take the derivative with respect to x, and that is equal to the derivative of the top, which is secant squared of x, times by the bottom, which is 1 plus cosine of x, alright, minus the top, which is tan of x, times by the derivative of the bottom, which is 1 plus, which is actually going to be negative sine of x, all over 1 plus cosine of x squared. Alright, what can we do here? Well, what I'm going to do is I'm just going to expand this out a little. So we're going to get, and I may or may not have to move some stuff around later, but that's fine. So secant squared times by 1 is still just secant squared of x. But times by cosine, that's just or secant of x. Secant of x. Minus, or sorry, plus tangent of x, sine of x, all over 1 plus cosine squared, and squared of x. Sadly, I don't think there's anything we can do with this, because the numerator, I could in theory pull out a 1 over cosine of x from everything, but that wouldn't particularly be worth it. So I'm just going to leave it as is and call this our final derivative. And when you look at that, we're a third of the way done. An hour in. So be prepared. This is probably going to be several hours of more derivatives, but at least it's a good opportunity for a lot of practice. Okay, for this next derivative, we have e to the power of 1 over x squared. Okay, once again, we take the derivative with respect to x. This is a quotient rule. However, I don't want it to be. So we're actually going to call this e to the 1 over x times by x to the negative 2. Now it's a product rule. I like product rules. I hate quotient rules. And this is what I do often on tests. I refuse to deal with it. So we take the derivative with respect to x. The derivative of the first is e to the 1 over x times by the derivative of its inside, which this is really just x to the negative 1 power. Its derivative then must be negative x to the negative 2 times by x to the negative 2 plus e to the 1 over x times by the derivative of the second, which is just negative 2x to the negative third. Alright, well, we get e to the 1 over x times by, adding up our exponents there, we get x to the negative fourth plus e to the 1 over x, or actually, minus 2 x to the negative 3. And that's our answer. Very messy, but it's technically right. Alright, next one. Q of x is equal to the natural log of secant of x. This isn't a product rule, it's a chain rule. So we take the derivative of the natural log with respect to secant of x, which is 1 over secant x, times by the derivative of secant. The derivative of secant is secant tangent. Secant of x, tangent of x. Our secants here will cancel, and as if the angels from heaven above are singing down upon you, you are left with just one beautiful tangent of x. This next one is a very messy implicit differentiation one, but we're still going to just take the derivative with respect to x. We are left with, in this one, dy dx plus the derivative of the first here is 1, so we get cosine of y, times by, or sorry, not times by, but plus the derivative, or the first, which is x, times by the derivative of the second, which is going to be a minus sine of x, which is sine of y in this case, times by the derivative of the inside function, is equal to the derivative of the first, which is 2x, times by the second, which is y, plus x squared times by dy dx. Now I have to bring all of these dy dx's to the other side, or to one side, which is a mess and a half, but we got to do it. So we get dy dx minus x sine of y dy dx is equal to, or sorry, minus x squared times by dy dx is equal to cosine of y, negative cosine of y, plus 2xy, and I think that's it. Now we have to factor this, so we are just going to erase all of these dy dx's, make my life a bit easier. undo that last one. Yeah, that's okay. So, yeah, I can just factor this out. I get a 1 minus there. Got to keep the 1. Undo. Alright, and then put in parentheses, dy dx. Divide this over, so we are left with dy dx is equal to negative cosine of y plus 2xy over 1 minus x sine of y minus x squared. Alright. Next problem. So we are going to start out in this problem by taking the derivative of the outside. So we get p prime of x is equal to negative 1 minus x to the negative 1. Alright. Well, if that's the case, then now we need to take the derivative of the inside. Well, the derivative of the inside is just going to be x to the negative 2, because the derivative of x to the negative 1 is negative 1 times by x to the negative 2. Times that by negative, that's going to become x to the negative 2. Alright. More implicit differentiation. Okay. We're going to take the derivative of this function with respect to x. The derivative of sine of xy is going to be equal to cosine of xy times by the derivative of this inside function. Well, the derivative of the first in this case, because this is a product rule, is just 1. So we get y plus the x times by the derivative of the first, which is dy dx, is equal to 2x minus dy dx. Okay, now what we have to do is we have to single out the dy dx's. So we get y cosine of xy plus x cosine of xy dy dx is equal to 2x minus dy dx. Alright. Now what we have to do is we have to get the dy dx's to one side. So, moving our work up here, we are going to get dy dx plus x cosine of xy times by dy dx is equal to 2x minus 2x minus y cosine of xy. Alright, now what do? We just factor out the dy dx. So we are left with this expression here. Now we just divide the 1 plus x cosine of xy to the other side. And we find our dy dx is equal to 2x minus y cosine of xy over 1 plus x cosine of xy. And that's our answer. For this next one, this one is a doozy. But we can work through it. To start out, never mind, this one's not a doozy. I was thinking of 40. So t prime of x is really the derivative of a logarithm is 1 over the natural log of its base, which in this case is 5, times by whatever is inside of it, so 1 plus 2x, times by the derivative of the inside, which in this case is 2. So that's our answer. Alright, next problem. is going to be the natural log of sine of x minus 1/2 sine squared of x. So the natural log of sine of x, or the derivative of that, is going to be 1 over sine x times by cosine of x. Okay, minus 1/2 times by 2 sine of x times by the derivative of this inside function, which is cosine of x. So this 1/2 and 2 will cancel. So what we're left with is cotangent of x minus sine of x cosine of x. Okay, for this next one, this one's an example of a power raised to a power. So we need to start out by taking the natural log of both sides. So we get the natural log of a of x is equal to the natural log of cosine of x raised to the power of x. Now we're going to use our exponent properties to bring this power of x up front. So we're now left with the natural log of a of x is equal to x natural log of cosine of x. Now what we have to do is we have to take the derivative of this with respect to x in order to find our derivative. So the derivative of the natural log of a with respect to x is a prime of x, the derivative of the inside, over 1a of x is equal to the derivative of this x here is 1, so we get the natural log of cosine of x times by, or sorry, not times by, but plus x over the derivative of the natural log of cosine of x is going to be 1 over cosine of x times by the derivative of cosine of x, which is negative sine of x. So what we're left with here is a prime of x over a of x is equal to the natural log of cosine of x plus, minus x tangent of x. Multiply this a over, and we know that a is actually cosine to the power of x. So what we are left with is this final expression for a prime. All right, moving on. We have y is equal to t tan inverse of 4t. All right, well, to start this one out, we know this is going to be the derivative of the first, which is 1. So tangent inverse of 4t plus plus t times by the derivative of tan inverse of 4t, which is 1 over 1 plus 4t squared is going to be 16t squared. And we can just move that t upstairs, and we will see our final answer because that can't be simplified anymore. All right, this next one. We have two composite functions here. So we have the derivative of e to the cosine of x. Well, this is the same thing as like the derivative of e to the x, just with respect to cosine of x. So we're going to say y prime in this case is going to be e cosine of x times by the derivative of this inside, which is negative sine of x. Okay, minus sine of x, because the derivative of cosine is sine, times by the derivative of the inside, which is e to the x. So in this case, y prime is equal to e cosine of x negative sine x minus or e to the x sine of e to the x. Okay. So now we are dealing with the natural log of arc sine of x squared. Well, in order to do this, this is a 3-link chain. So what we're going to do is we're going to take the derivative with respect to x. So we're going to get y prime is equal to the derivative of natural log of x with respect to arc sine of x squared is just 1 over arc sine of x squared. Now I have to take the times by the derivative of the inside, which is 1 over the square root of 1 minus x to the 4th, because we're dealing with like x squared. But now I also have to take the times by the derivative of the inside, which is 2x. No matter what way you cut this isn't going to get any simpler than this. So you can always combine these fractions, but this is as simple as it's going to get. This next one is another 3-link chain here. So we're going to take the derivative of this with respect to theta. We're going to get y prime. Well, the derivative of tangent squared is just 2 tangent of sine theta. Okay. Times by the derivative of tangent is secant. So we get secant squared of sine theta. The derivative of sine is cosine of theta. And this here is our answer. Of course, in theory, you can always write this out in the forms of sines and cosines, but I would never want that for you. Alright, this next one. So we want to find f double prime of pi over 6 for g of theta is sine of, or g of theta is equal to theta sine of theta. Alright, so this is more like, okay, this is more application based. I like that. So, let's see. So, g prime of theta, we're going to need to take the derivative of this with respect to theta. Well, the derivative of the first in this case is just 1, so we get a sine theta. Plus the theta times by cosine theta. Alright, now if we want the second derivative, we have to take the derivative of that with respect to theta. So we get g double prime of theta is equal to, well, sine of theta, the derivative of sine of theta is cosine of theta, plus the derivative of this first, which is 1, so we just get cosine of theta again, plus the derivative, or plus the first, times by the derivative of the second, which is negative sine theta. So we get g double prime of theta is equal to 2 cosines of theta plus or minus theta sine theta. Now we just have to plug and chug. Well, we know that 2 minus cosine theta. Well, cosine of pi over 6 is, well, 2 times by square root of 3 over 2 minus pi over 6 times by 1/2. We get square root of 3 minus pi over 12. And that's our answer. Alright, next problem. Find y double prime if x to the 6th plus y to the 6th is equal to 1. Okay, this is going to be a mess. Be ready. So, of course, we start out by taking the derivative of x to the 6th, which is 6x to the 5th, plus the derivative of y to the 6th, which is 6y to the 5th, is equal to 0. Actually, it's times by the derivative with respect to y, or the derivative of y with respect to x is equal to 0. Now we're going to move this 6x to the 5th to the other side. So we're going to get negative 6x to the 5th is equal to 6y to the 5th dy dx. Now we're going to divide both sides by this 6y to the 5th. So we are left with negative 6x to the 5th over 6y to the 5th is equal to dy dx is negative x cubed, or x to the 5th over y to the 5th. Alright. Now we need to find the second derivative. So we once again take the derivative with respect to x of this. This time this is going to be a quotient rule. So the derivative of the first here. So we take the derivative of the top, which is negative 5x to the 4th times by the bottom, y to the 5th, minus the derivative of, minus the top, which is in this case going to be plus x to the 5th, times by the derivative of the bottom, which is 5y dy dx, all over y to the 10th. Now what are we going to do, you may ask? Well, what I think I want to do is I'm going to start out by canceling this y to the 4th and making that y to the 5th just a bit smaller. So we're going to drop the power of this y down to a 6th, and that y is just now y. We know dy dx is actually equal to negative x to the 5th y to the 5th over y to the 5th. So now what I want to do is I'm going to multiply through by y to the 5th on both the denominator and the numerator. And I'm going to distribute this, so I get y to the 6th, or negative 5x to the 4th, y to the 6th, plus, minus minus 4x to the power of 5 all over y to the 11th. Now what I'm going to do is I'm going to factor out, or actually, no, because that's going to, never mind. This should be the furthest simplified form of this. So this is our dy dx squared, or the second derivative of y with respect to x. Alright, onward and forward. Find the tangent line and the normal line to the following. Ooh, this is a mess, isn't it? So, the tangent line is just the line that's representative. Well, it's the line that touches the curve at the point. The normal line, however, I'm sorry, just had to take a short break, is the line that's perpendicular to the tangent line. So, just remember that y in, or really slope normal, is equal to negative 1 over m. Okay. So we're going to take the derivative of this first function. So we get y prime is equal to 8 sine of x cosine of x, using the chain rule. Then we need to plug in pi over 6. Actually, here's a better option. Actually, no, yeah. Pi over 6. Yeah, pi over 6. Y prime is equal to 8 sine 8 sine of x cosine of x. Okay. Plug in pi over 6, we get y prime evaluated at pi over 6 is equal to, well, 8 sine at pi over 6 is just 1/2 times by the square root of 3 over 2. We will be left with just 2 square roots of 3. So if we want our equations of our normal line and our tangent line, so we can get y tangent minus 1 is equal to, 2 square roots of 3 times by x minus pi over 6. And then if we want our y normal, it's going to follow the exact same like bone structure, except for it's going to be negative 1 over 2 square roots of 3 times by x minus pi over 6. Alright, next problem. Oop, this one does not have a point, so... Give me a moment. You know what? We're just going to think of a generalized expression for this, which is going to kind of be interesting to see how this shapes out. So, we're going to start out by taking the derivative of this. So, we can get y prime is equal to, well, the derivative of the top in this case is going to be 2x times by the bottom, which is x squared plus 1, minus the top, which is x squared minus 1, times by the derivative of the bottom, which is 2x, all over x squared plus 1 squared. What do I want to do with this, now you might ask? Well, we're going to find a very interesting equation. So we're going to say y minus x squared minus 1 over x squared plus 1, as this is going to give us our x coordinate for any point, is equal to all of this jazz. Let's see. Actually, I think I found a way to simplify this just a little. So I'm going to rewrite this. Factor out the 2x times by, well, we're going to subtract out these x squared minus x squared is going to be 0. However, we're going to get a minus 2 in there over x squared plus 1 squared. So we're just going to have a negative 4x times by x squared plus 1 squared times by x minus whatever value of a you plug into this. So interestingly enough, this expression here, and I should probably change a lot of these to a's, is going to give you a equation of a line anywhere on a curve. Interestingly enough. So if you want a tangent line, all you have to do is plug in a value a into this equation and work it out, and that will give you the tangent line. Now, if you want the y normal for that, it's just the exact same equation, except for this part's going to be the reciprocal. And I'm sorry this is a bit more abstract. I was not intending for that problem to be. I just forgot the coordinates that I wanted to use for that. And I personally don't want to pick coordinates that work out nice. So, this next one. We're at number 50. We're halfway there. At this rate, we'll be done in 3 hours. That is scary. I don't want to be up that late, but it's fine. We take the derivative of the outside. 1/2 all over the square root of 1 plus 4 sine x. The derivative of the inside, which is just going to be 4 cosine of x. Alright. Now what do we do, you may ask? Now we just have to plug in 0. What is cosine of 0, you may ask? It is 1, so we get 4 over. Sine of 0 is 1, so we just get 4 over 2. That's going to be 2. And we know that this is going to be equal to 1. Okay, never mind, I don't know how that works. So we are going to get y minus 1 is equal to 2x minus 0. So it's just 2x. Cool. Alright. Now we need to find f in terms of g prime. So this is just really going through some rules and some properties. So this first one, we're going over the product rule. So f prime of x in this case is going to be 2x g of x plus x squared g prime of x. Okay, nothing too scary there. Next one is a composite function, so this is a chain rule, so f prime of x in this case is equal to g prime of x squared times by 2x. The next one is again a composite function, however this time g is on the inside, so we take 2 g of x times by the derivative of g with respect to x, which is g prime of x. For the final one, we get f of x, or f prime of x, is equal to the derivative of g with respect to g, which is g prime of g of x, times by the derivative of g, which is just g prime of x. Alright, a lot of g's there. Now we need to find the h prime of the following functions. Again, using primarily just function notation here. Very strong test of like your product rule and your quotient rule. So for this first one, we need to take the derivative of the top, because this is a quotient, and this is a very messy one at that. So the derivative of the top is f of x times, f prime of x times by g of x plus f of x times by g prime of x. Okay, that's just the derivative of the top times by g of x minus the derivative, minus the top, which is f of x times by g of x times by the bottom, which is f of x, or the derivative of the bottom, which is f prime of x plus g prime of x, all over f of x plus g of x. Does this simplify? Do I want to find out? No. No, thank you. In fact, I don't think this can simplify in any way, shape, or form. So I'm just going to leave this be. if you want to try and simplify it, you can. So, for this next one, we have h of x is equal to the square root of f of x over 2 of x, or g of x, sorry. So, in this case, and I probably should have said this up here, taking the derivative with respect to x, you never want to say is equal to its derivative, as it is not true. However, if you say the derivative of that is equal to the derivative, then that is true, and as thus you can say that. Important thing to note whenever you're doing math. So we take the derivative with respect to x, and this is going to lead us to get 1/2 the square root of all that jazz, which in all honesty, what I'm going to do real quickly is this is just going to be the same thing as f of x raised to the 1/2 power, but it's going to be in the denominator. So we're going to call this the square root of g of x over the square root of f of x times by the derivative of the inside, or the derivative of the inside function, which is going to be the derivative of the top, which is f prime of x, times by the bottom, which is g of x, minus the derivative of, the top, f of x, times by the derivative of the bottom, g of x, g prime of x, all over g of x squared. Wonderful. Now onward. For the next one, we have h of x is equal to f of g of sine of x. Oh, that is hefty. So we take the derivative with respect to x of both sides. So we get h prime of x is equal to the derivative of the outside function, which is f prime of g of sine of 4x, times by the derivative of the inside function, which is g prime of sine of 4x, times by the derivative of the inside function, which is cosine of 4x, times by the derivative of that, which is 4. That is a 4-link chain. That is a mess, but that's our answer for you. All right, moving on. So, what point on the curve is the natural log of x plus 4 squared tangent to the horizontal? Good question. Is there even one? Is another good question. Well, we'll find out. So, what does it mean to be tangent to the horizontal? Is the tangent horizontal? Well, that means that the tangent is going to have a slope of 0. So we need to solve y prime for 0. So that's where we're going to start. We're going to find dy dx. Well, we need to take the derivative of the outside, which is 2 natural log of x plus 4, times by the derivative of the inside, which is just 1 over x plus 4. And we can see here that we need to solve this numerator for when it's equal to 0. So, 2 natural log of x plus 4 is equal to 0. Well, I can divide both sides by 2, and I'd get the natural log of x plus 4 is equal to 0. Raise both sides to the power of e. So I get e to the 0 is equal to x plus 4. And finally, after subtracting the x plus 4 to the other side, we get 1 minus 4, or is equal to negative 3. So we now need to find the point that corresponds to negative 3. So we get the natural log of 1, which is 0, So 0. Negative 3 comma 0. Interestingly enough, is going to be the point where y is horizontal. The tangent of y is horizontal. Alright. So if a cube has its side lengths x and it expands as time passes, find dv dt in terms of dx dt. So we know volume of a cube is given by its side lengths cubed. Well, it's actually called cubed, interestingly enough. So what we need to do is we need to take the derivative of this with respect to time, since we know that its side lengths x are expanding. So we get dv dt is equal to 3x squared dx dt. And that's our expression. If the edge of the cube is increasing by 4 centimeters per second, how fast is the volume growing if the edge length is 15 centimeters? Okay. Well, this is now just a plug and chug. So we know that our dv dt is going to be equal to 15 squared times by 4. 15 squared is, if I can remember my squares correctly, 225. Times that by 4 is like 900, right? Yeah, 900, I would think. So its volume is going to be growing by 900. I suppose this is centimeters cubed per minute or per second. Very fast growing cube. Alright. The radius of a spherical ball is increasing at a rate of 2 centimeters per second. At what speed is the surface area of the ball increasing? Okay. Good questions here. So the surface area of a ball is given by 4 pi r squared. So I suppose this was probably wanting like at 5 when the radius is 5 or something. So we'll just say that is 5 centimeters. Okay. So we're going to take the derivative of this with respect to with respect to t. So we get our dA dt is equal to 8 pi r dr dt. We know this dr dt is 2, so we get dA dt is really just equal to 16 pi times by 5. Well, what is 16 times by 5? 6 times by 5 is 30. That would be 80 pi. 80 pi centimeters squared per second. Alright, next problem, and all of these problems here that we're doing at related rates. A cylindrical tank with radius 5 is being filled with water at a rate of 3 meters per minute. How fast is the height increasing? Okay, good question. Well, volume of a cylinder is given by pi r squared times by height. So we know that this is volume is pi r cubed, or pi r squared, times by height. So we know that this r, the radius, is fixed. So it's not changing. But we know the height is. So we're going to take the derivative of this with respect to t. So we get v prime is equal to, well, this r squared is just a constant, so we're going to leave it be. It's in fact 5 squared, which is going to be 25 pi dh dt. We know that the volume of this is changing at a rate of 3 meters per minute. So 3 is equal to 25 pi dh dt. So we can find our dh dt is equal to 3 divided by 25 pi. And that gives us our answer of how fast it's increasing. Alright. You're looking at an airplane traveling 400 miles per hour towards you. It flies 6 miles above the ground. Find the rate of change of the angle of elevation of you looking at the airplane. So I think this is best done with the diagram. So we start by sketching, let's say a graph almost. And we have this airplane in the distance. And you're just the guy down here looking at this airplane. But because the airplane's so high, we'll just say that you're probably really down here. You don't have to account for your own height in this case. We want to know, how is this angle theta changing if this airplane is 6 miles above the ground and it's traveling at a rate of 400 miles per hour. Okay. Well, how do we approach this? Well, we want something that's going to relate our x value here and our opposite value here. And the way that we're going to do that is by using a tangent or a cotangent, whichever we so choose. So I'm going to choose to do a cotangent because it will keep the x in the numerator. So, cotangent of theta is equal to, we know that cotangent is going to be adjacent over opposite. Now we can multiply the 6 to the other side to get 6 cotangent of theta of x. Now we have a relationship between our cotangent and whatever distance this airplane is. Well, it's important for us to realize that no matter what way we're thinking about it, this airplane's coming towards us. Our distance is getting smaller, and as thus, this should be a negative 400 miles per hour. And we're going to use that in a moment to find the rate at which our angle of elevation you're looking at the airplane is changing. So, now what we're going to do is we're going to take the derivative of this with respect to time. Because this rate up here is really just a dx dt. So once we get that, we get dx dt, not dx dx, dx dt is equal to 6, or negative 6, cosecant of theta cotangent of theta times by, or d theta dt negative. There we go. Now what we need to do is, this is just a constant rate, so we're just going to plug in negative 400, cancel those negatives, so we get 400 over 6 cosecant theta, cotangent theta, is really the rate at change our d theta dt is changing. So if we want to know whenever our theta is equal to, let's say, pi over 6 degrees, we can find that the answer to that question is going to be pi over 6 of cosecant is going to be times by 2, and cotangent of pi over 6 is going to be the square root of 3. So that would be our answer if we did pi over 6. Also, I lied, this should be the square root of 2. Because it's going to be 1 over the square root of 2, but because we're taking the reciprocal of sine. No, it should be 2, because sine at that point is just 1/2. Okay, yeah. 2. So 12 square roots of 3. And then if you want, you can simplify that down to 100 divided by 3 square roots of 3. Alright, find the equation of the tangent lines given the point. Okay. So I believe it's almost at this point where I've started doing more application derivative stuff, but I'm not sure. So f prime of x in this case is 3x squared minus 2x. Plug in negative 2. F prime of negative 2 is equal to 12 plus 4. So f prime of negative 2 is equal to 16. Okay. Now what do we do with this information? Well, we are now just need to construct an equation of the tangent line. So we need to plug in f of negative 2 as well to find our f value. So f of negative 2, or x cubed of negative 2, is just negative 8 minus 4 plus 3. So f of negative 2 is equal to negative 9. So our answer is going to be y plus 9 is equal to 16x plus 2. And that would be our answer. Once again, f of 0 here is equal to e to the 0, which is just 1. F prime of x is 3e to the 3x. So f prime of 0 is 3. So our answer in this case is y minus 1 is equal to 3 times by x. And that would be our answer for approximation. So now we need to find the differential, the error, and the relative error of the following. Well, to start out, we need to take the derivative of this. So we find dy dx is equal to 2x minus 4. Then from this, we can derive our differential. So our change in y, in theory, is going to be 2x minus 4. And we want to approximate this change in x with our dy. So we're going to just plug in x is equal to 3. So dy is equal to 6. Change in dy dx. There it is. So we have 6 minus 4, which is 2, times by 1/2 is equal to 1. So for a change of x of 0.5, when when x is equal to 3, that the expected change in y is 1. So now we want to take the relative error, the error and then the relative error of the following. So to find the error, we are going to... Alright, so I realized that I was calling this the wrong thing. So I want to call this the relative change and the percent change instead of the error and the percent error. The absolute change and the relative change. So the absolute change is just going to be found by taking this dy and dividing it by y. So what you'll see is if we plug in 3 for this value, we'd get 9 minus 12, so we'd get negative 3 over 1. So that would be negative 0.333. Now for this relative change, we just need to multiply this by 100. So we're going to get 1 over negative 3 times by 100 is equal to 33, or negative 33. It might be an absolute value, but I don't believe so. But 33 times by, or not times by, but 0.333 repeating. Alright. Next one. So we have dy is going to be 1 minus 3x squared times by our dx. We know our x is 0, but our change in x is negative 0.3. So our dy is going to be equal to negative 0.3. Okay, now what do we do? Well, we just need to divide this by the actual value at 0, which is 0. So interestingly enough, this one you can't really find a relative error for, or an absolute change, or a relative change for. For this next one, we need to find the derivative, which in this case is going to be dy dx is going to be 1/2 the square root of x minus 2. However, we're going to multiply that dx over, and now we're just going to estimate using our dx's. So we get a 0.8 divided by 2. So we get an estimated change of 0.4. Now we're going to take that 0.4 divided by the actual, which is just 1. So our percent error is going to be 0.4. I mean, not percent error, but the absolute change. And then the relative change is going to, again, just be that the dy divided by the y times by 100. So it's going to be 40%. All right. Now what do we do? Okay, so now we're on to find the local and the absolute extrema that of the function on the given interval. Okay. So for this first one, 68, we're going to start out by taking the derivative. So we get y prime is equal to 3x squared minus 18x plus 24. All right, now what do we do? We want to see if that's factorable. And indeed, it does factor. So we get y prime is equal to 3x minus 4 times by x minus 2. Okay, now what do we do? Well, we now have our candidates for our extrema. We know that there's not going to be any undefined values in that area, so we're just going to see how our function is behaving. So I'm not going to go through the full justification of why in this video. I'm just going to state like where there's an absolute min or an absolute max. So let's see. If we know that this is going way out in the negatives, but really it's not, we're just going to say like 1. Both -4 and -2 are going to be negative, so it's going to be positive. At 3, however, only one's going to be negative, so it's going to be negative. At 4, both of them are going to be positive, so it's going to be positive. So we have a candidate for a relative max at 2 and a relative min at 4. But there can also be one at 0 or 5. So we have to test all of these values to find where the relative extrema are. So f of 0, in this case, is just 0. F of 2 is equal to 18. F of 4 is 14. F of 5 is 18. So it will have an absolute max of y is equal to 18, relative max of relative max at the point 218, not 28, 218, and 518. All right. It will have a absolute min at 0, 0, and it will have a relative min at 0, 0, or sorry, absolute min of y is equal to 0 and a relative min of 0, 0 and 414. All right. For the next function, once again, we have to take its derivative. So we get y prime is equal to the derivative of the first, which is 1. So we get the square root of 1 minus x plus x over 2 square roots, or minus, sorry, 1 minus x. So now we have to find some values that are going to make this equal to 0. So I think what I want to do is I'm going to try making this all into one or one big function here. So y prime is going to be equal to 2 over 2 square root of 1 minus x times by the square root of 1 minus x over the square root of 1 minus x minus x over 2 square root of 1 minus x. Great, now I got it. So things can get kind of canceled here. So what we're left with is 2 minus 2x minus x all over 2 square root of 1 minus x. All right, now what do we do? Well, we can combine some bit more like terms and get negative 3x. All right. And since that's the case, what we'll see is we can now solve the numerator and the denominator for potential inflection points. So we get 1 So we get 2 minus 3x is equal to 0. Well, then negative 3x must be equal to 2, or negative 2. So x must be equal to 2/3, must be 1. And the other might be 2 square roots of 1 minus x is equal to 0. So the square root of 1 minus x must be equal to 0. Square both sides, so we get 1 minus x is equal to 0. And then finally subtract the 1 over. We get negative 1 is equal to negative x, so x might be equal to 1. That's the other candidate. So we plot those points on a graph, 2/3 and 1, as well as our other point of extrema, which is negative 1. Pretty far away from the rest. So we're going to do a small bit of a test. So if we plug in, let's say, a value less than 2/3, so let's say we plug in like negative, well, let's say we plug in just something a small bit smaller. It makes my math easier. So this numerator is going to be negative, but this denominator is still going to be positive. So this is going to be negative. From 2/3 to 1, well, let's see. From 2/3 to 1, this numerator is going to be, or actually, sorry, I lied. Because it's going to be slightly smaller than 2/3, it's going to be like 1/3 or something like that. So this is actually going to be positive, and as soon as it gets to 2/3, it's going to flip to negative, because it's going to, the negative 3x is going to be bigger than the 2, so it's going to go to negative. And then it doesn't matter what happens at 1. So now we just have to plug in these potential points and see if any of them are, or which of them is maxes and which of them is mins. So f of negative 1 is equal to negative square root of 2. Alright, f of 2/3, which is where a potential maximum might be, is going to be 2/3 times by the square root of 1/3, which is like 2 over the square root of 3. Simplifying that, we get 9 over the square root of 3. I believe that will be a small bit bigger than just the square root of 2. I might be wrong, though. And of course, we always have a calculator check. F of 1 is equal to, well, 0. So without a doubt, we have an absolute min of y is equal to 0. Relative min of negative 1 square root of 2. Oh wait, no, that's a negative square root of 2. Negative square root of 2 needs to be the absolute min. Sorry, I misread my own work. Alright, so we get negative 1 negative square root of 2, and then comma the other point, which is going to be 1 and 0. Then we have a absolute max of 2 square root of 3 over 9, and then the coordinates of that are going to be 2/3 2 square roots of 3 over 9. Alrighty, for this last function, once again we take the derivative, so y prime is going to be equal to 1 plus 1 minus 2 sine of x. on the interval from negative pi to pi. So what we're going to do is we're going to solve this for 0. So 0 is equal to 1 minus 2 sine of x. Subtract that over, so we get negative 1 is equal to negative 2 sine of x. And apparently I'm going to have to erase some stuff, but I'll do that in a moment. So 1/2 is equal to sine of x. And sine of x is going to be 1/2 whenever x is at pi over 6 or 5 pi over 6. So those are going to be our answers. So x needs to be 5 pi over 6 or pi over 6 in the other order. Okay. Alright, now we are going to start a number line going from, or number line going from negative pi, pi over 6, 5 pi over 6, and then pi. At negative pi, our original function is, well, negative pi. I'd assume that would, no matter what value of cosine that takes, which it will be negative 1, that is still going to be like negative, very negative. Then at like pi over 6, we get, let's say I plug in pi over 6, that would be 2. Cosine of pi over 6 is square root of 3. Oh wait, no, I'm plugging that into the wrong thing. I'm sorry. So, sorry. I don't know, I keep apologizing, I say that a lot. So, if I plug in negative pi into our y prime, well, actually, no, I don't. Yeah, that works because that's not one of our actual critical points. So, from negative 1, sine at negative pi is 0, so we're just left with a positive number 1. So it's positive. At pi over 6, it's going to become negative. Or at pi over 6, yeah, that's going to become like a small bit bigger than 1/2. Times that by 2, it's going to be a small bit bigger than 1. So yes, it's going to be negative. Then at 5 pi over 6, it's going to go back to being a small bit smaller than 1/2. So whenever the 1's still going to be bigger. So it's going to be positive. Okay. Now we just have to plug and chug to see where our absolute mins and our absolute maxes are. So, f of negative pi is equal to negative pi minus 2. Cosine of negative pi, yeah, is negative 1. Okay. F of pi over 6 is equal to pi over 6 plus square root of 3. F of 5 pi over 6 is 5 pi over 6 once again. This time, however, minus the square root of 3. And then f of pi is just going to be pi minus 2. Okay. Now I'm going to real quickly just assign approximations to these values. Alright, I got approximations for those values here. So we can now clearly see that it will have a absolute min of y is equal to negative 5.1, 5.1, a relative min at the point, or at negative pi, negative 5.1, and 5 pi over 6.9, and then it will have a relative max, or a max, of 2.3, of y is equal to 2.3, 2.3, and then a relative max of 2 point of pi over 6, 2.3, and then 1 point pi 1.4. All right. Alrighty, so we have quite a few more minimum and maximum problems here. So we're going to go through these, find their mins and their maxes. Oh wait, actually no, we only have one more of those, and then we have some limits. So we have 71, which is y is equal to x squared e to the power of negative x on the interval from negative 1 to 3. So what are we going to do? We start by taking the derivative with respect to x. So y prime in this case is going to be 2x e to the negative x minus x squared e to the negative x. Okay, now what do we do? Now we just need to solve this expression for zeros. So I think the easiest way to do this is to factor out an e to the negative x. So we get y prime is equal to x e to the negative x times by 2 minus x. And now we know that x e to the x, e to the negative x, must be equal to 0. So we can divide the e to the negative x over, but that would just be x is equal to 0. Or 2 minus x is equal to 0, so x must be equal to 2. Those are candidates for either for extrema on the interval. So we're going from negative 1 to 3, but also with 0 and 2 in between. So, then actually I'm going to just do 0 and 2 here, and then do negative 1 and 3 on the ends. So if we plug in a really big negative number, even though it's outside the interval, it will still tell us what's happening outside of this 0. We will see that y prime will be negative because this x is going to be negative, but this one's going to be positive. So we're going to be decreasing. From 0 to 2, if we plug in something like 1, it will be positive because x e to the power of negative x is, or 1 times by e to the negative 1 is just a positive, and then times that by another positive, so we know that's increasing. And finally, from 2 to 3, we can just plug in a really big positive number, and what you'll see is it's going to be negative because this x e to the negative x is going to be positive, but this 2 minus a really big positive number is going to be negative. So now we just have to plug in our points. So we have f of negative 1, which is going to be e, f of negative, f of 0 is 0, f of f of 2 is going to be 4 e to the negative 2, and f of 3 is going to be equal to 9 e to the negative 3. Alright. So, which one of these is the smallest value that we experience? Well, in this case, it is going to be this 0, and I'm going to write out approximations for all of these. So we can see after plugging in these points, the function on this interval is going to have a absolute min of y is equal to 0. It will have a max, or an absolute max, of 2, or sorry, of 0.5. Or sorry, actually. So it has an absolute max of 2.7. And I guess you can kind of intuitively derive that because it's going to be in somewhere the negative plane where e is going to be positive and so is x squared. So it's going to probably be the biggest, but I digress. This is more about the calculus here. We are going to have a relative min of 0, comma 0, and if I can find it, yeah, just 0, comma 0, as technically this 3 won't count, even if it's their smallest value. And then a relative max of, well, of course it's going to be negative 1. And then, yeah, negative 1, 2.7. And then 2, comma 0.5. Okay. Next up on the list is L'Hospital's rule, or L'Hopital's rule. So, because this derivative is going to be of the form 0, or, yeah, it's going to be 0 over 0, we're going to take the derivative of the numerator and the derivative of the denominator, noting that it's not a quotient rule. So we are going to get the limit as x approaches 0 of 2 e to the 2x minus, plus 2 e to the negative 2x all over 1 over x plus 1. If we take the limit as this now goes to 0, we get, well, in the denominator, that's just going to be 1 over, or under, rather. If we plug in 0, the e is going to be 0, so it's going to be 2 plus 2, so our answer is 4. Right, next one. So, interestingly enough, this derivative that we have here, or this limit that we have here, is not in the normal form that we have. This one is more specifically in the form of an infinity, more specifically a negative infinity, times by 0. But I believe we can make this into an infinity over infinity indeterminate form. how are we going to do that, you might ask? Well, we are going to just use some properties here. So we're going to say that this is going to be the limit as x approaches negative infinity of x squared minus x cubed over e to the negative 2x. Now, our original function wasn't in a form that L'Hospital's rule could be used, but this is. Because now as we go to negative infinity, the numerator is going to go to infinity, and the denominator is also going to go to infinity. So now what we're going to do is we're going to take the derivative of the top and the bottom. So the derivative of the top in this case is going to be 2x minus 3x squared over negative 2 e to the negative 2x. Now we're going to take the limit as this limit approaches negative infinity. Okay. Now what are we going to do with this? Well, if we plug in bigger and bigger numbers here, I suppose, actually, in this form, it's a bit easier to reason out that because e to the power of negative 2x, in this case, will have a higher magnitude than a cubic, we can argue that this e to the negative 2x will get bigger at a faster rate than the numerator, so this limit is going to approach 0. Limit as x approaches negative infinity is going to be 0. And I suppose I could have derived that at the very beginning. Alright, next up on the list. Oh, did I do the same problem twice? I did. You know what? We are actually going to change this just a little bit. We're going to say that as the limit goes to infinity. So, for this problem here, we're going to once again want to treat this like L'Hospital's rule. So we are going to get x squared minus x cubed over e to a negative 2x. Well, if we want to know what number this is going to approach as it goes to infinity, let's take the derivative of this. Well, actually, let's see if it actually qualifies. But I don't think it does, because it'll be a negative infinity. Okay. So, actually what I want to treat this really as is more or less a magnitude problem. If not, it doesn't even matter. So this limit, as x approaches infinity, of x squared minus x cubed of e to the 2x, that's just going to approach infinity. It's going to be an infinite, well, in fact, that's actually going to approach negative infinity. As we plug in really big values of x, this inside function is going to be negative, and this function is going to be positive, and this limit's not going to approach any real number. So it's just going to go to negative infinity. Alright. For this next one, we wanted to know what the limit as x approaches 1 from the right is of x over x minus 1 minus 1 over the natural log of x. So to start this problem out, I think what we want to do is cross multiply this and see how that changes our function. So we're going to get the limit as x approaches 1 from the positive direction of x natural log of x minus 1 over x, the natural log of x times by x minus 1. Okay, Now if we plug in 1 here, we get 1 times by the natural log of 1, which in that case is 0, minus 1, so that didn't do any good, over the natural log of x times by x minus 1, which would be over 0. What can we do here? So this is going to be x minus, or x plus 1. So, because that is brought up, okay. So, this is actually, this numerator is going to become 0, and this denominator is also going to be 0. So this is a 0 over 0 indeterminate form, so we can use L'Hopital's rule. So we're going to take the limit as x approaches 1 from the right of the derivative of the top and bottom. So we get the derivative. What's the derivative of a product? It's going to be the first times by the second plus the first times by the derivative of the second, which in this case is just 1, minus the derivative of x, which is going to be minus 1, all over the natural log of x. Looks like a product down there, so we get a natural log of x for the first, which is 1 over x, times by x minus 1, plus natural log of x. Now if we plug in 1 here, we get this function is going to go to be 1. However, this natural log of x is going to be 0. Or this is going to be 0. That's going to be 0. This top part is still going to be 0. So we're going to take the derivative of this again. Okay. So we get the limit as x approaches 1 from the positive direction of 1 over x over, I'm going to kind of just divide this out, the derivative with respect to x of 1 minus x to the negative 1 plus the natural log of x, taking the derivative of this, or doing the derivative of that, we are left with 1 over x divided by 1 minus, x to the negative 2 plus 1 over x. Now if we plug in 1 for all of these values, you will see that we get 1 over 1, which is just 1, divided by the 1 raised to the negative 2 power, which is still 1, plus 1, so our final answer is 1/2. Kind of a doozy to get to that. Alright, so now I have a bit of graph sketching using derivatives. So this is really just testing what you know of, like, the properties of the derivative. So gotta get this graph sketched out. Normally I use white for graph sketching. Alright. So the first property of the graph that we see is f of 0 is 0. Okay. we know f prime of negative 2, f prime of 1, and f prime of 9 are all equal to 0. So those are all important points that we want to have marked on our graph. 4, 5, 6, 7, 8, 9. Alright. And we know the limit as x goes to infinity is going to be 0, so we're going to draw out a horizontal asymptote. We don't know what happens as it goes to negative infinity, so we can do some creative liberties there. The limit as x approaches 6 of f of x is equal to negative infinity. So 1, 2, 3, 4, 5, 6. We know that there's going to be a vertical asymptote here. Alright, now what do we do? Well, we have several points that we know are 0, or have going to be critical points, really. So we have f prime of negative 2. So I'm just going to draw a little horizontal line. Another horizontal line somewhere on f of 0, or f prime of 1. And then finally we have f prime of 9, which is very far away from the rest. 9. Alright. Now all we have to do is sketch out a curve with the following conditions. So I'm going to do this in my, I don't know what color this is. But in this case right here, and because we know the limit does exist and it's negative infinity, this must be a horizontal, a vertical asymptote. And this is what your graph may or may not look like. Of course, there's a lot of different things you can do with this graph. You don't have to put the critical points where I put the critical points, but you can. Alright, this next graph that we're drawing has a lot more work to do with concavity and derivatives. So once again, we start out by sketching our graph, drawing our axes, and we need to make sure that we have enough coordinates to support everything that's there. So it looks like this has a range of 12. So we go 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13. You might want to do it just a small bit farther than your highest value. Okay, and then looks like for our smallest value we have negative 2, so I'll go to negative 3. 3. And of course, you don't really have to mark your y-intercept, although it's recommended. So here's what we know. We know that, and please note that the reason why, even though f is increasing, the reason why these endpoints are not included on the interval is because this is saying when f prime is less than 0, not less than or equal to. So to think about this in increasing or decreasing, f would be increasing from negative infinity to including 2. So what we're going to do here is, I think I want to make a number line, just 2 number lines in fact, just so I can kind of visualize all of this data. So we know that from negative infinity to 2, actually scratch that, it's going to be negative infinity to negative 2, I believe. Yeah, there we go, that fixes it. So from negative infinity to negative 2. And then our next point of interest is going to be at 1. Then our next point of interest is going to be at 6. And then our next point of interest will be at 9. And then we just have our negative infinity and our positive infinity. We know at negative infinity to negative 2, it's less than 0, so it's decreasing. From negative 2 to 1... Alright, from negative 2 to 1... it is going to be positive. Okay? From 1 to 6, it's going to be negative. Then at 6 to 9, it's going to be positive, and then 9 to infinity, it's going to be negative. Okay. Now on the exact same, or on a different set, but using hopefully the exact same scale almost, I want to use this graph to visualize the concavity of it. So we have 0 here. And then looks like we have negative infinity 0, and then 12 to infinity 0 to 6. Okay. So from 0 to 6, 6 to 12. And then that goes to infinity. So we, over here, from like negative infinity to 0, you can see that this graph needs to be concave up, or its second derivative is positive. From 12 to infinity, it's also positive. However, from 0 to 6, it is negative, as well as 6 to 12. Alright. 2, 4, 6, 8, 10, 12, 13. Yep, okay. So what are we going to do with this information? Well, this is going to help us sketch out our graph. So we can mark out at negative 2 that there is going to be at least some kind of 0 there, more than likely a minimum. So we're actually just going to slightly place it underneath the graph. Then at 1, there's going to be some kind of maximum. Then at 6, there's again going to be some kind of minimum. Then at 9, there will be the final maximum. And then it's going to be going down to, or it's going to be decreasing. And it also should be decreasing way over here. There we go. Okay. Now let's look at the concavity of the graph. So, we know that this graph is going to be concave up from negative infinity to 0. So, we sketch our graph, making sure to kind of make it look like it's a bowl. And that's going to keep going up and up and up until we reach 0, in which case it's going to start looking more like a downward concavity. And then this downward concavity is going to continue now that looks concave up. This is a very interesting from 0 to 6, and there's a critical point at 6. Interesting, so... Okay. Well, this is just a... You know what? We're going to move the critical point down a little bit. There we go. And then it's going to go back up. And I don't think there's a way to visually make that. Well, yeah, never mind. That does look concave down on both sides. And that looks like it has a slope of 0. And then finally, it goes down to negative infinity at the very end. And that would be a close graph of this function. Alright. Ooh, actually, you know what? I have an idea on why this point's like this. Actually, I believe there's an asymptote right here. As that's the only way I could probably foresee that it being concave down, but not at that point. Alright. So now we're going to review a bit of Newton's method, or do a few problems with Newton's method, which states that x to the n is equal to, or n plus 1 is equal to x to the n minus f of x of the n over f prime of x to the n. And this general thing is going to be what's going to help us approximate the square root. So the first thing we need to ask ourselves is, what function is going to have a 0 at this point? And so that's what Newton's method does. It approximates zeros. So what we're going to do is, we know that this can easily be shown as a difference of squares. So, or it can be shown as like the function of x minus the square root of 7. And if we really want an easy function, we can just multiply it by its conjugate. So we will get x squared, or y is equal to x squared minus 7. So now what we're going to do is we're going to take the derivative of this, so we get y prime is equal to x to the n, or sorry, no, it's equal to 2x. So we're going to say x to the n plus 1 is going to be equal to x to the n minus x squared minus 7 over 2x to the n. Alright. Now all we have to do is plug this into our calculator, and we are going to say my starting guess for the value of 7 x to the n, or x1 is equal to, let's say, 2.5. Alright. So, take our calculator, and actually give me a moment. So what we're going to do, and this is kind of looks like a TI-84 calculator, it has all the same inputs. So we are going to say that we are going to take 2.5, 2.5, and we're going to store that as x. If I can figure out how to store variables as x. Ah, never mind, wrong x. Alpha x, if I can find x, there it is. Store as x, enter. Then we are going to go to do x minus, and we're going to go to y vars, and this is just leftovers from a very long time ago. And a video I was doing on the inverse trig function. Surprised it's still there. And we are going to input the graph of x squared x no back please, x squared minus 7, and then for our y2, 2x. Alright, now we're going to quit out of this page. We're going to go to vars, y vars, function 0 of x divide that by, oh no, I accidentally deleted it. Here, give me a moment and I'll get back. Alright, and then you're going to go divided by vars y1 of x of this bottom x here. And we are going to hit enter. Never mind, that did not want to work the way that it should have. Or maybe it did. And then I want to store that. Okay. I'm going to make sure I did the right x for each of those. So I think what I want to do is, give me one moment. Alrighty, so that problem was not working. But hopefully you saw the way to input it into your own calculator. So we're going to go into your calculator, do 2.5. Make sure that you have x squared minus 7 in your y1, and then 2x in your y2. Then you're going to hit quit. You're going to go to our... So you're going to have it punch into your calculator. You're going to hit enter, and it's going to give you a bit better of an approximation. So our x2 in this case is 2.65. Then you're going to use that approximation to get an even better approximation. 2.646. And then you're going to use that approximation to get an even better approximation. And it looks like it only took 3 renditions to get the exact same answer twice in a row. Or at least to like 6 decimal places, which is kind of impressive. So now we're going to use Newton's method to find the zero of the following. So we have y is equal to x cubed minus x squared minus 1. So what we're going to do here is we're going to find y prime, and that's going to be 3x squared minus 2x. Alright, now what do? We make a guess for our first x1 is going to be, let's say, positive 1. And now we just need to put in like our x of n is, or x minus y of y1 of x over y2 of x, store it as x into our calculator, and then run that command as many times as it takes to get however many decimal places of accuracy. After running the command, I got 2. is x2 is 2. x3 is 1.625. Our x4 is 1.486. Our x5 is equal to 1.465. And then our x6 is equal to 1.46. This should also be a 6. And you can now see that we now have agreement in like 3 places of decimals, which is accurate enough for us. Alright. This is optimization problems now, I believe. So what is the maximum vertical distance between x squared plus 1 and x minus x squared? Now this is kind of interesting, but I have a theory that there is not a max vertical distance, but we're going to test that out. Okay, so to start out, we're going to subtract them, and we know that because this x squared is going to make it go way down into the negatives, I propose that this x squared plus 1 is going to be the higher of the two. In fact, this graph is going to look something like this. And we want to know what this vertical distance is, or what maximizes said vertical distance. So we're going to take, and we're going to find a new function, g of x, which is going to be x squared plus 1 minus x plus x squared. Alright, g of x, or g prime of x, no, we just want to simplify g of x right now, is going to be 2x squared minus x plus 1. Taking the derivative of that, we get g prime of x is equal to 4x minus 1. Alright, so now we need to find, or now we are going to do a number line, and we're going to solve this equation for 0, so we can find zeros. 4x minus 1 is equal to 0. So 1 is equal to 4x, so x is equal to 1/4. Okay. Well, before it's equal to 1/4, that's going to be negative. But after, it's going to be positive. So, the only critical point we have is a minimum. So, because of that, we know that there's not going to be a maximum vertical distance between the two. However, in theory, we can find the closest that they ever get, which we just have to plug in 1/4 into our original equation there, and we would get a number that I don't feel like solving for, because that's not the question we asked. So there is no max distance. Is no max distance, as it's just going to keep getting further and further away. So a perimeter of a rectangle is 100 meters. What dimensions make the area as large as possible? So this one, we know that there's going to be 2x plus 2y is equal to 100. And we want to know what's going to make x times by y have the largest area. Or area of x. I suppose I can call it area. So what we're going to do is, because I don't want to work in functions with multivariables, we are going to find a way to substitute, in this y for a x instead. So we're going to get 2y is equal to 100 minus 2x. Then we're going to divide both sides by 2, so we get 50 minus x. And then we're going to plug this into our area function. So a of x is equal to x times by 50 minus x. Then what we're going to do is we're going to multiply this out so we get a of x is equal to 50x minus x squared. Okay. Then what do we do after that? Well, now we're in a proper state to find the maximum or the minimum of this. So, a prime of x is equal to 50 minus x. Okay. Let's draw our number line. 50 minus x is equal to 0. When negative x is equal to negative 50, so x must be equal to 50. Okay, what happens before 50? Well, if we're at 49, it goes positive. But if we're past that, it goes negative. So this is a possible maximum for the function. Of course, we also have to have our endpoints. Well, let's think about it this way. Can a rectangle ever have an area of 0 or have a dimension of 0? I don't think so, because that'd just be a line. Or can... Well, its domain, really. Let's think about its domain here. Well, it's... Let's see, how do I want to say this? X really can't be 0, so it must be 0. But X also can't be 100, or I suppose 50, because there must be 2 of them. So we're going to take the limit of the function as it approaches 0 and 50 to find the values, and the limit as x approaches 0 of a of x is equal to 0, and the limit as x approaches 50 is also 0. So, what we are left with here is one critical point. Oh, wait. Give me a moment. How intriguing. So 50 should be the maximum, but it's not. Give me a moment. Oh, I know what I did. I know what I did wrong. This needs to be a 50 minus 2x. So this value here is actually 25. There we go. Now, what do we do with this? So, we now know the maximum area is going to be at 25, because it has a max and the other 2 possible points are 0. So we plug in this 25 into our original area function. So we get... Or actually, no, we don't want to plug it into our original area function. We want to plug it into our perimeter function. So we know x, it's going to be... x is equal to 25 meters. And if there's 2 of them, that just leaves... Well, let's see. This would be 50 plus 2y is equal to 100. So y must be 25 meters. So it's a square. The square is what's going to maximize that area. Alright. A box with an open top is to be constructed. Apparently I can't spell. There's a reason why I don't want a degree in English. Constructed from a 4x3 piece of cardboard by cutting out squares from each corner, then bending them up the side to make the sides. Find the max volume of the box. Okay, so I think a diagram's always helpful to start out with. So there's these little squares that are x by x in each corner. And each of these squares is, and each of these sides is 4 feet. I believe this was supposed to be in feet. I don't remember. Feet by 3 feet. Okay. So we want the thing that's going to maximize the volume here. So we know the area of this rectangle is given by 3 minus 2x. And then also 4 minus 2x. Alright. Volume in this case is going to be, let's see. Yeah, volume is just going to be x times by 3 minus 2x times by 4 minus 2x. Now let's get some bounds on this. So we know that we don't want any of these side lengths to be negative or 0. So we want 3 minus 2x to be greater than 0. So we get negative 2x must be greater than 0 than negative 3. Divide both sides by negative 2. So we get x must be less than 3. Okay. Now let's also run the same test for this 4 minus 2x. So 4 minus 2x must be less or greater than 0. So we subtract the 4 over, so we get negative 2x is greater than negative 4. Then we're going to divide both sides by negative 2, so we get x must be less than 2. So because this condition is more restrictive than this condition, we're going to choose this condition. So our domain is going to be from 0 to 2. Alright, well, now we're going to multiply this function out, so we get v is equal to 12x minus 6x squared minus 8x squared plus 4x cubed. Then if that's the case, then v of x must be equal to 12x minus 14x squared plus 4x cubed. Take the derivative of that, so we can now find its mins and its maxes. V prime is equal to 12 minus 28x plus 12x. Now what do we do with this? Or x squared, sorry. Now we need to solve this function for 0, so we're going to actually plug this into our calculator. So we go to y is equal to, we clear out all of our previous stuff, and we say 12 minus 28x plus 12x squared. Alright, and then you're going to hit format, or sorry, not format, but window, and you're going to set your min to 0, your x min to 0, and your x max to 2. And you are going to, I believe my y min and y max are kind of strange. I want it to be like 1 and 0. There we go. Window 1, min of negative 1 to a max of 1. There we go. Yeah, now I can see this. So the function actually crosses the x-axis twice in those 2 points. Second 0. So at one point, it goes from a positive to a negative. So that would be its possible max. So at x is equal to 0.566. All right. All right. And then now let's find the coordinate of, or actually we shouldn't need to find the coordinate of the other point because we know that's going to be a minimum because the derivative goes from negative to positive. So normally you have to justify this, but I'm not going to in this video, just as the purpose of saving time since we're on hour 3 almost. So we now just have to find the maximum volume of the box. We just have to plug this value into our function up here. Okay, and after plugging that into our volume formula, you'll get volume of 0.566 is equal to 3.032. And that would be our maximum volume for a box of this size. How interesting. Alright. So now we want to find the point on the line y is equal to 2x plus 3 that is closest to the origin. I don't think an origin has an e, but I'm not a English teacher here. So I'm going to start out by sketching the graph. And this graph is going to look something such as this. And the origin is right here. If we want to know, this is really a distance problem. So we want to know what point on this line, we can call this x f of x. X f of x is closest to this point. So if we want to know the distance between this is just the x value and the value of f of x. And then the distance of this between the two is going to be the square root of x squared plus f of x squared. Okay. Well, we know that what our x is, and so we just need to find out what our 2x plus, or not really, we don't need to find that out, but we just need to find the derivative of this and then minimize it. So the distance is equal to that. We want to plug in our function, so x squared is the square root of, well, we have 2x plus 3, so plus 4x squared plus the sum of the two, twice the sum, which would be 6x, so 12x, I think. Give me a moment. So that's twice the product, which is 12x in this case, and then plus 9. So our distance in this case is going to be the square root of, let's see, 5x squared plus 12x plus 9. Now we can actually do a nice little trick here, and we can say whatever value minimizes this inside function is also going to minimize the square root. So we're going to call this d hat is equal to really just 5x squared plus 12x plus 9. We're then going to take the derivative of that. So we get d hat, the derivative of d hat dx is equal to 10x plus 12. Then we just have to solve that for 0. So we get d hat of dx is equal to, 0 is equal to 10x plus 12. So subtract the 12 over, so we get 10x. X must be negative 6/5. All right. So about negative 1.2 is going to be the point closest to the origin. So now we just have to find the point. So we know that it's going to be negative 1.5. So negative 1.2, not 1.5, I apologize. And then what's 6? That'd be negative 12/5. So we have negative 12/5 plus 3, which I want to get you into fifths, so that's 15/5. So that's going to be 3/5 or 0.6 on our original function. That would be the point that's closest to the origin. For this next one, we want to find the curve, find the point on the curve square root of x that is closest to the point 3 0. Okay. Alrighty, well, we're now on to question 84. So, find the point on the curve y is equal to the square root of x that is closest to the point 3 0. So I think it's always helpful to draw out a little diagram, especially for these point problems. Alright. To kind of just get a grasp of what we're looking at here. So we're really looking at a triangle with a base of x minus 3 and a height of the square root of x. So this distance between the points, distance is going to be the square root of x minus 3 squared, which is x squared minus 6x plus 9, plus the square root of x squared, which is x. So we get for our distance, it's going to be the square root of x squared minus 5x plus 9. Well, now I think it's important for us to realize the same value that's going to minimize this inside function is going to be the same value that minimizes this outside function, the square root. So what we're going to do is we're going to determine a new function called d hat, which is equal to the square root of x, or not the square root of, but x squared minus 5x plus 9. Then we're going to find the derivative of d hat with respect to x, which is 2x minus 5. Now what we're going to do is we're going to graph this, or not really graph this, but place this on a number line. And we can go to the point, let's see, that would be 5 is equal to 2x, so x must be equal to 5/2. Alright. So if x is smaller than 5/2, then x is going, if x is smaller than 5/2, x is going to be negative. If it's bigger than, it's going to be positive. As thus, we can say that this value here, this 5/2, is going to be the minimum. So now we just have to plug this into the original to find the point. So we're going to have 5/2, comma, square root of 5/2 as the point on the square root of x that's closest to 3, 0. And interestingly enough, I think that does make some sense. This final problem is actually kind of interesting in the fact that this is using implicit differentiation. And most of the problems that I've encountered don't actually use implicit differentiation. So this ellipse problem is also good practice for seeing something new. So we want to find the points on an ellipse 4x squared plus y squared is equal to 4 that are farthest away from the point 1, 0. Okay. So, let's see. How do we want to work this? Well, we know the distance formula. So the distance from anything is, it's going to be the square root of and we'll call our x to this ellipse. Hopefully that will work. Well, I'm going to start out by graphing this, putting this on a graph so we can see what we're looking like here. So this parabola, or not parabola, but this ellipse is going to go 1 out in the x direction and 2 out in the y direction. So we're going to get an ellipse that generally looks something like this. And then we have this point right here. Well, if we, or 1, 0, sorry, I realized that was the wrong point, down here. So if I want the distance of this point here to another point on this curve, well, this is going to be the same thing as the point on the curve, or sorry, our x value here is going to be 1 minus our x value of the point. Okay. Our y value, however, y is 0, so we know it's going to be 0 minus our y value of the point, which is going to be given by y squared plus 4x squared. Oh, this is a challenge. Okay. Is equal to 4. You know what? We're going to just say it's equal to y. And I may or may not be able to get something out of that. Now, this x-coordinate is correspondent to 4. So, what I'm going to do is we're going to subtract the y squared minus the 4x squared plus 4. And that's going to give us our y value of the curve. So now what we need to do is we need to plug this into a function, or plug this into our distance formula. So we're going to get distance is going to be equal to the square root of 1 minus x squared plus y squared minus 4x squared plus 4. Now what do we do? Well, we need our distance to be equal to the square root of 1 minus 2x plus x squared plus y to the 4th, Or minus y to the fourth, I apologize. Minus 4x squared, or sorry, minus, oh, this is a pain in the buttocks to square out. Give me a moment. So what we get by expanding this out is 16 x to the fourth minus 8x squared y squared minus 32x squared, all right, plus y to the fourth plus 8y squared plus 16. Now, there's a lot of room for mistakes here. So what we're going to do is we're going to take the derivative, or we're going to once again call a function d hat, and we're going to just plug in this abomination to it. So we get d hat is 1 minus 2x, or actually, give me a moment. All right, so our final answer is 16 x to the fourth for d hat minus 8 x squared y squared minus 31x squared minus 2x plus y to the fourth plus 8y squared plus 17. Okay. Now we have to take the derivative of this abomination. So d hat prime is going to be 64x cubed minus, well, the derivative of the first here is going to be 16x y squared. All right. And then our derivative of the second is going to be let's see, 8x squared y squared, or 2y, so grand total is 16, dy dx, all right, minus 62x minus 2 plus 4y dy dx cubed on the y plus 16y there's no real way of minimizing this. I messed up somewhere, but that happens. So I'm actually going to start doing a different approach because this distance formula may or may not work. So what we're going to do is we're going to divide this down into two different parts. We're going to find the y squared of both of these. So we get y is equal to 4 minus 4x squared. So y squared, or y must be equal to the square root of 4 minus 4x squared, plus or minus. And now I can work on two different distance formulas. So d is going to be equal to the square root of 1 minus x times, squared plus 4 minus 4x squared. And then we have another distance formula of the square root of 1 minus x squared minus 4 plus 4x squared. All right. So now what do we do with this? So what we're going to do is we're going to let's call this D1 and D2. We're going to expand this out just a little bit and then simplify. So we get D1 is equal to the square root of 1 minus 2x plus x squared plus 4 minus 4x squared. And then for D2, we get a square root of 1 minus 2x plus x squared minus 4 plus 4x squared. Then we can kind of simplify this a little. So we get D1 is equal to the square root of negative 4x squared minus 2x plus 5. And we get a D2 of a square root of a negative 3. Well, actually, let's bring this coefficient. So we have 4x squared minus 2x minus 3. Then what we have to do after that is now we need to find the derivative of both of these. But we're going to use the same derivative trick that we have been using and call d hat is equal to negative 4x squared minus 2x plus 5. And d2 hat is really going to be 4x squared minus 2x minus 3. Now we need to take the derivative of both of these. So we get d1 prime is equal to negative 8x minus 2. And we get d2 prime is equal to, let's see, this would be 4x squared minus 2x, 8x minus 2. Now we just have to solve both of these for 0. So we get d prime, or let's actually just put this on a number line real quick. So we want to move this negative 8 to the other side. So we get negative 8x, or 8x, is equal to negative 2. So x must be equal to negative 1/4. All right. So we plot negative 1/4 for x's that are smaller than negative 1/4. Well, x is going to be, like if I plug in, it's going to be positive. But for x's bigger than negative 1/4, let's say something like 3, it's going to be negative. Coming over to the other side now, we have to also solve this equation. So we get negative 8x is equal to negative 2. So we get 1/4 for our solution to this equation. So if x is smaller than 1/4, let's say like -2, 8x minus 2 is going to be negative, so it's going to be decreasing. And then from 8x minus 2, if x is greater than 1/4, then it's going to be increasing. So if we want the points that are farthest away from this ellipse, we are going to want the points that maximize the distance. So we're going to be looking at -1/4 rather than +1/4. So when we're looking at -1/4, as from the if we're looking at -1/4, because that is a maximum, it's going to maximize the distance. What we're going to see is whenever we plug it into our equation, y is going to be equal to plus or minus the square root of 4 minus 4 times by 1/4 squared. So y is equal to plus or -1/4 rather, but plus or minus the square root of 4 minus 1/4. So like 3.75 is going to be, yeah, that would be the x coordinate of our point. And then y is equal to then whatever the square root of that number is. And we get an answer of 1.936. So the points that are furthest away from the curve are going to be plus or minus 1.396. So -1/4, 1.936, and 1/4, 1.936. And those would be the points. So for the next following problems, we're just going to be doing some first and second derivatives, working through them. Not too hard. Alright, so give me one moment and we'll get started. Alrighty, so the derivative of f of t of e to the power of 3t is really just 3e to the 3t. Then the derivative of that is 9e to the 3t. For this next one, it's the derivative of a quotient. So y prime, in this case, is going to be the derivative of the top, which is 1/2 the square root of t, times by the bottom, which is t squared plus 1, minus the square root of t times by 2t over t squared plus 1 squared. Now what do we do with this? Well, I like my things very simplified, so I'm going to multiply through the top and bottom by square root of t. Actually, you know what? No, we're not going to do that. We're just going to keep working. So y double prime is equal to the derivative of the top, which is going to be a bit of a mess, but that's okay. So we're going to use parentheses to separate. The derivative of this first is another quotient. It's t squared plus 1 over 2 square roots of t. However, I'm going to make it so this is not a quotient and just say that this is, or rather, what I'm going to do is I'm going to say this expression is equivalent to 1/2 t to the power of 3/2 plus 1/2 t to the 1/2 power, or to the negative 1/2 power, minus the square root of t of t to the 3/2. Let's call it t to the 3/2. All over the chain rule, which is going to be t squared plus 1. Got it. So now if I take the derivative of this to get y double prime, we get the derivative of the top, which is going to be 3/4 t to the 1/2 minus 1/4 t to the negative 3/2 minus 2 t, or sorry, not 2, but 6 t to the 1/2 times by the bottom, which is t squared plus 1 minus the derivative of, or square that, minus the derivative of, minus the top, which is 1/2 t, which is 3/2 t to the power of the 3/2 plus 1/2 t to the negative 1/2 times by the derivative of the bottom. I suppose I should maybe move this. Alrighty, so it's going to be times by the derivative of the bottom, which is going to be 2 times by t squared plus 1 times by the derivative of the inside, which is 2t, all over t squared plus 1 to the power of 4. And now I can cancel one of these t to the, or t plus 1s to make it t cubed. So all we are left with is this final expression, which in theory you can simplify if you want. I'm not going to. For this next one, this is just a power rule, so y is going to be equal to x, or y prime is equal to ex to the e minus 1. Y double prime is going to be equal to e times by e minus 1 x e minus 2, and that would be our answer. Alright. For this next derivative, it is another example of a quotient rule. I really hope something might cancel in here, but I'm pretty sure it won't. But hey, it's worth a try. So we want to see if anything is equal to 8 but adds to 3. Is there any numbers that do that? 2, 4, no. No, there is not. So, what we have to do is we just have to do the derivatives. So f prime in this case of x, well, the derivative of the top is just 1, so we get 2 plus 3x plus 4x squared minus the derivative of the top, or not the derivative of the top, but the top, times by the derivative of the bottom, which in this case is going to be 3 plus 4, or 8x. And that is over 2 plus 3x plus 4x squared to the power, or squared. Alright. Well, then what's
let's maybe simplify this a little bit. Get one consolidated expression up top. So we get 2 plus 3x plus 4x squared minus 3 minus 8x minus 3x minus 8x squared. All over the bottom expression of 2 plus 3x plus 4x squared. Alright, now what we're going to do is we are going to combine everything together. This 3x and this 3x will cancel. So we are going to be left with we are going to be left with a -1, or rather a -4x squared minus 8x minus 1 all over 2 plus 3x plus 9x squared. Alright, and that's our f prime in its like simplified form there. Now we have to take the derivative of that. So I'm going to move this somewhere so I can have a bit more, or rather I'm going to clear this out so I can have a bit more space. Alright. So we need to first start out by taking the derivative of the top, which is going to be 8x minus 8 times by the bottom, which is 2 plus 3x plus 9x squared minus the top, which is -4x squared minus 8x minus 1 times by the derivative of the bottom, which is 2, times by the inside function, which is 2 plus 3x plus 9x squared, times by the derivative of the inside, which I'm going to kind of just write underneath it, times by 3 plus 18x. Or sorry, not 18. That's supposed to be a 4x. So it's going to be 3 plus 4, or 8x, all over 2 plus 3x plus 4x squared. And that would be our answer. For this next one, we're going to start out by distributing that theta, just to make our lives easier. So we get theta plus 1, y prime, and then is going to just be 1, and y double prime is 0. Makes it easy. We're going to take the derivative of this with respect to y. So we get f prime of y is equal to 1 over the natural log of 3y cubed times by the derivative of the inside, which is 1 over 3y cubed, times by the derivative of the most inside function, which is going to be 9y squared dy. Yeah, never mind, just 9y squared. So then, if that's the case, we can cancel this 9 and this 3, leaving 3y squared, and then we can cancel this y squared out entirely, and we are left with an expression of 3 over y natural log of 3y cubed. Alright, now what do we do? Well, we are going to then take the derivative of this expression, which is now a product, or is now a quotient rule in theory. So we get f prime of y, or f double prime of y, is equal to the derivative of the top in this case is 0, so we just get minus the derivative, or the top, minus the derivative of the bottom, which here is a product rule. The derivative of the first with respect to y is going to be 1, so we get the natural log of 3y cubed minus y minus, let's see, the y times by the derivative of the natural logarithm, so 1 over 3y cubed times by the derivative of the inside, which is going to be 9y squared. This y squared and this y cubed and that y are all going to cancel, leaving just 3 in its wake. So all over y natural log of 3y cubed squared. And that's our final answer. For this next one, we get y prime is equal to 0. The derivative of e to the negative pi is just a constant, 0, and pi to the power of negative e is just a constant. And because y prime is equal to 0, y double prime is also equal to 0. Alright, this next one is technically a 3-link chain, but no, wait, yeah, it would be 3-link. So we have p prime of t is going to be the derivative of the outside, which is 2 cosine of 3t plus 5, times by the derivative of the inside, which is sine of 3t plus 5, times by the derivative of that, which is 3. Then now to find, and we're going to just bring this 3 out front and make that a 6. P double prime, in this case of t, is going to be a product rule. So we are going to get the derivative of cosine is negative sine, so we are going to get negative 6 cosine of 3t plus 5 times by the derivative of 3t, which is just 3, times by sine of 3t plus 5 plus 6 cosine of 3t plus 5 times by the derivative of sine, which is cosine of 3t plus 5 times by the derivative of the inside, which is 3. Now we just have to simplify this, and we get p double prime of t is equal to negative 18 cosine of 3t plus 5 is negative 3t sine. And since we're multiplying these two signs, it's just going to be sine squared. And then we have plus 18 cosine squared of 3t plus 5. Alright, and that's our answer. Sadly, even though we may want to, we can't use the Pythagorean identity to make that just like negative 18, because it's adding when they shouldn't be added. Alright, so sine theta is equal to sine squared of theta 3 theta minus pi. Okay, that's a mess. So let's see. S prime of theta is going to be 2 sine of 3 theta minus pi times by the derivative of the inside, so cosine theta of 3 theta, sorry, of theta, 3 theta minus pi times by the derivative of the inside of that, which is going to give us 6. S double prime in this case, well, we take the derivative with respect to theta again. Well, the derivative of the first here is going to be 6 cosine of 3 theta minus pi times by the derivative of the inside, which is 3, times by the second, which is cosine of 3 theta minus pi, plus the derivative, plus the first, which is going to be sine theta, 6 sine of 3 theta minus pi times by the derivative of the second, which is negative sine of 3 theta minus pi times by 3. So what we are left with is, gotta go somewhere else to write this because I'm short on space here. We get 18 cosine of 3 theta minus pi minus 18 sine of 3 theta minus pi. Alright. Next one, we have the square root of theta squared minus sine squared of 2 theta. So, q prime of theta, in this case, is going to be 1/2 the square root of 4 theta squared minus sine squared of theta, sine squared of 2 theta, alright, times by the derivative of the inside function, which is going to be 8 theta minus 2 sine of 2 theta times by cosine of 2 theta alright, and then times by the derivative of the inside of that, which is 2, so we're going to get a negative 4 sine theta. Now we have an expression for our q prime. Now let's try and find an expression for our q double prime of theta. So, this is going to be kind of a mess, but we can do it. We know theta, or we have 8 theta times by 4 sine of 2 theta. We have to take the derivative of the top first, which this is going to be a very messy product. Oh wait, no, this should be a plus, not a times. It should be minus. Oh, I'm pretty sure I accidentally erased a part of that. Okay. So, we get the derivative of the top, which is going to be 8 minus 4 cosine of 2 theta. Alright. Cosine squared of 2 theta minus Okay, minus. Alright, it's going to be plus, actually. The derivative of, plus 4 sine eight sine of 2 theta squared times by the bottom, which is 1/2 the square root of 4 theta squared minus sine squared of theta. Alright. Or minus the top, which is just 8 theta minus 4 sine of 2 theta cosine of 2 theta times by the derivative of the bottom, which we already know is this abomination right here. So it's going to really just be 1/4 8 theta. I'm going to have to close that. Eight theta minus 4 sine squared theta cosine, not cosine squared, cosine of 2 theta. It's cosine of 2 theta. You can't see it, but I wrote it all over. All over the square root of 4 theta squared minus sine squared theta all over the denominator squared, which is going to give us 4 times by 4 theta squared minus sine squared of 2 theta. So this denominator is going to simplify to 16 theta squared minus 4 sine squared of 2 theta. Alright. Next up on the chopping block, g of t of arctangent of 3t minus 4. Alright, well, g prime of t in this case is equal to, the derivative of the top is just going to be 3, and then in the denominator we're going to have 1 plus 3t minus 4 squared. Well, if that's true, then we're going to have 3 over 1 plus 9t squared minus 24, I believe, t minus 16. So our final answer here is going to be 3 over 9t squared minus 24t minus 15, and then we can cancel this 3, and we're going to be left with this as our final answer. Now we just have to take the derivative of that, which is a lot easier of a derivative to take. So it looks like we are going to get negative 3t 3t, or the derivative of 3t squared, which is going to be 6t plus 8 all over 3t squared minus 8t minus 5, and that would be our g double prime. Next up we have m of n is equal to sine of e to the n. We take the derivative with respect to n, so m prime of n is equal to cosine of e to the n times by the derivative of the inside, which is just e to the n. M double prime of n is equal to, well, the derivative of the first is going to be negative sine of e to the n times by the derivative of the inside, which is going to be e to the n, times by e to the n. We're going to just add the exponents there and say e to the 2n plus cosine of e to the n times by e to the n. And that would be our answer. We got another implicit differentiation problem. So we have, I don't believe these ones. I wanted to find the first and second derivatives. I just want the first. So we have 3x squared plus 3y squared dy dx minus 8xy minus 4x squared dy dx is equal to 0. So then we're going to subtract all of these terms without a dy dx to the other side. So we get 3y squared dy dx minus 4x squared dy dx is equal to negative 3x squared plus 8xy. And that is equal to, or that's not equal to anything. Now we're going to factor out a dy dx from this left side and then divide over. So we get dy dx times by that is equal to that. So dy dx must be equal to negative 3x squared plus 8xy all over 3y squared minus 4x squared. And that would be our answer. Alrighty, for this next one. Well, we know this left side is just 1. The cosine squared of y plus sine squared of y is just 1, is equal to y plus 2. Take the derivative of that with respect to x, and we get dy dx. Well, we have 0. So we find the derivative of y with respect to x is just 0. So the function's not growing at all. In fact, you can see that this is just a constant. Alright, so I have a little note over here that y is equal to dt dx. So in this case, we're trying to find a function y from this derivative. So let's get started. So the derivative of t with respect to x is equal to, well, I'm going to bring this 1 over r squared out front. It's going to be times by the derivative, or this first function. So just x, which the derivative of is 1, times by the second function, which is the natural log of x over m, minus as, minus x, or sorry, no, that's not a part of it, plus the first, which is x ams All right. Natural log, or the derivative of the natural log of x over m minus as minus as. Oh, I forgot to put this like under something. There we go. Times it. Minus 1. Well, now what are we going to do with this function? Well, this dt dx is going to be 1 over r squared times by the natural log of x over m minus as plus x minus ams over x over m minus ams, or not ams, but as, minus 1. Now I would like to multiply the bottom and the top of this by m. Is equal to 1 over r squared of the natural log of x over m minus as. All right. So I realized that I was Alrighty, so then we are going to subtract off this this m. We're going to use some of our rules of fractions here, all over r squared, to find that dt dx is the natural log of x minus ams all over m. Well, 1 over r squared times by x minus ams over 1 times by the reciprocal, which is m over x minus ams. This and this will cancel, leaving an m, and then we have minus m over r squared. So this entire thing over here cancels. So we are left with dt dx is equal to the natural log of x minus ams over m. And we know that dt dx is actually just y. Now I kind of want to, and this is over r squared. We are going to multiply this r squared over to the other side, so we get y r squared is equal to the natural log of x minus ams. Then we are going to, over m, then we're going to raise both sides to the e power. So we are going to then get e to the yr squared is equal to x minus ams over m. We will then multiply the m to the other side. So we get me to the yr squared is equal to x minus ams. After a small bit of rewriting, I'd like to end off by saying Merry Xmas. Merry Christmas to all. I hope y'all really had fun with this video. I know I did. I know I'm not the best when it comes to problems, but especially if I'm improving it. A lot of these problems was my first time working through them, and I noticed that some of the problems that I created often had a small bit of errors in them, but that is okay. Well, I hope all of you have a wonderful rest of your day. I hope you all had a great Christmas and enjoyed this video. And if you found me informative, I hope y'all would leave a like for the 5 hours of work I've put into this. I hope y'all have a great day.